Have you ever wondered how computers count? Probably not, but today we'll be covering exactly that. In order to best understand how computers count, let's go back to your toddler years and review how we as humans learned how to count. I know this can seem obvious, but stick with me because I promise it will make interpreting binary numbers easier when we get to it. Imagine we just have one digit. When we rotate through all the possible combinations for this digit, we have 10 possible combinations, 0 through 9. Now let's imagine a two-digit number, let's say 11 for example. Now let's break down 11 into two separate digits. The leftmost digit being 1, and the rightmost digit also being 1 in this case. We can see that on the left side, the left one represents the tens place, while the right one represents the ones place. One interesting characteristic we can note right now is that the left digit is 10 times that of the right digit, and vice versa, the right digit is 1/10 of the left digit. We can see that even if our number was 3 digits long, such as 111, this property still applies, with each digit being 10 times the digit to the right of it, or 1/10 the digit to the left of it. We call this system of counting the decimal system, with deci meaning 10, because of how each digit can be 10 different possible values. Another way of writing this is the base 10 system. The leading theory is that because us humans have 10 different fingers to count on, we intuitively have had each digit be 10 different possible numbers. Though there are a few cultures out there, for those who may be interested, that don't have a base 10 system. However, computers don't have this base 10 system to rely on, but rather have a base 2 system. This is also known as the binary number system, with bi meaning 2. Let's explore this system. Similar to the decimal system, imagine you have a single digit. One digit in binary can be one of two numbers, 0 or 1. If we had two digits, we could represent four states, 0, 0, 0, 1, 1, 0, or 1, 1. Keep this in the back of your mind for now. Seeing just zeros and ones can be pretty abstract, so it's good to ground ourselves in what these numbers actually mean and how they have some meaning to us within the decimal system. So let's cover how to quickly translate these numbers from binary to decimal. Imagine we have a single digit in the ones place in binary. Let's say the number 1. Let's label this number as being in the ones place, with this blue 1 underneath it. All we have to do is take the place of that number to the power of the binary number. So in this case, we would take 1 to the power of 1. That would equal 1. Let's try it also with the binary 0. With the binary 0, we have our place, which is the ones place, to the power of 0, which equals 0. Let's try a larger number. Let's say we have a binary 1, 1. We have the ones place, but how would we define the next place? In decimal, this would be the tens place, as we discussed before, and the one to the left of that would be the hundreds place. But since we aren't in a base 10 system, and rather a base 2 system, this would be the twos place. This shift can be pretty odd at first, but with practice it becomes pretty natural. If we add another digit, it would be the fours place. Adding another digit to the left of it would be the eights place, and so on and so forth, but let's not get ahead of ourselves. Let's just work with two numbers for now, and how we would translate this to a decimal. Let's start with the twos place. 2 to the power of 1 is equal to 2. Now let's move over to the ones place. 1 to the power of 1 is equal to 1. Adding these two numbers together, we get 3 in decimal. So essentially, 1, 1 in binary is equal to 3 in decimal. Pretty cool. However, looking at this paper can be pretty confusing to anyone else looking at our work. I mean, 10, 11 equals 3, it looks pretty weird. Since it can be easily confusing to differentiate between binary numbers and their decimal counterparts, we typically use this prefix 0b before the binary number to indicate, well, that's a binary number. As you can see, our binary number is after our prefix. Similar to what we saw in the decimal system, we see that each digit on the left is 2 times the digit of its right. Similar to how we broke down our numbers in the decimal system, we can also break down our numbers within the binary system too. So in this case, our binary 11 can be broken down into binary 1, 0 and binary 0, 1. With our left digit, our 1, 0 being equal to 2, and our right digit, 0, 1 equal to 1. Similar to what we saw in the decimal system, digits are 2 times that of the digit to the right, or half that of the digit to the left. However, due to the constraints of binary numbers, we do run into some problems with our current definition. So far, we've discussed the positive numbers in a vacuum, but how would we define a negative number? So far, if we add binary 0 and binary 0 to each other, we are given 0. Similarly, if we add a binary 1 to a binary 0, we get binary 1. However, if we add two binary 1s together, similar to how you would carry the 1 within the decimal addition, you can think of this overflowing value to the next digit. We're going past our maximum value, so adding 2 1s is equal to 1 1 in binary, because we can only hold 0 or 1. If we add binary 1s, we get a 0 and have to carry the 1 to the next digit. Similar to how you carry in decimal addition, we carry our overflow value over to the next digit when we go past the maximum value that can be held in that digit. In decimal addition, this is 9. In binary addition, this is 1. Carrying the 1 over, we get a final result of 1, 0, which is decimal 2. That's cool, but we haven't really defined what negative 2 is. Essentially, there is no definition, but we are constrained to defining it as some sort of bit value so that we would be able to differentiate between a positive and negative value in binary. So what's an easy way that we can make our positive and negative value in binary representations look different? One way we could differentiate our negative numbers is to define the sign of our binary number through the leading bit. If the leading bit is 0, then the value is positive. If the leading bit is 1, then it is negative. This method was used in early computers, and it's called the sign magnitude representation. Some of the earliest computers, this was included the IBM 7090, for those who might be familiar. A better way to describe these bits would be the leading bit is most commonly called the most significant bit, or the acronym MSB, or the first bit is often called the least significant bit, or LSB. Going back to the negative number discussion, let's try some basic addition with our new definition. In the decimal system, adding 2 and negative 2 gives 0. However, doing our addition here, we also get 0. Interestingly, our definition allows for negative and positive zeros, which is a little bit strange, but we'll get back to this later. For now, we're getting 0 in some capacity, so it looks like our definition lines up with what the decimal math is adding up to. However, let's see what happens when we add 3 and negative 3. Oddly enough, adding 3 and negative 3, we come out with negative 2. Adding numbers here does not consistently give the value we expect in decimal, so we need to go back to the drawing board to come up with a better definition for how to define negative numbers in binary. One way we can ensure that our numbers add up to 0 is that our negative numbers are bit flip versions of our positive numbers. That way, whenever we do the addition of these two same numbers, we always get 0. This definition of negative numbers is called 1's complement, as we are defining our value 1 in this case, and its complement, negative 1. However, notice how, even in this definition, we still have this weird definition of a positive and negative 0 popping back up. However, similar to the last definition, all of our negative values still have the most significant bit 0 for positive numbers and 1 for negative values. Applying this to 1, negative 1, we will always get 0, although in this case, we end up with a negative 0, which is odd. When adding not-like terms like 5 and negative 3, we get a value of negative 1, which is close to our expected value of 2, but it's off by 1. This happens pretty often. For example, adding 6 and negative 2 gives us 3, which is off from the true answer of 4. In 1's complement, adding 1 is required in some cases in order to get the right answer. Visually looking at the table of 1's complement, we can see adding is always 1 off. Adding 4 and negative 3 gives us positive 0. Adding 5 and negative 2 gives 2. We can solve this off by 1 error by simply just defining one binary 0 and shifting up all the values from there. Now we can see that 5 and negative 3 add up to 2. This representation is called 2's complement, and that's largely how binary integers are interpreted today. However, notice how we've defined our integers. All of this is done simply by merging those zeros into one value, and we magically solve our off by 1 error. What if we were limited to say 8 bits, or 1 byte, and we were only going to have positive integers anyways? Having half our space wasted by negative numbers wouldn't be ideal. For that reason, lower level languages like C, C++, and Rust have different interpretations of the same underlying binary value, depending on what type it is defined as. In this example, we can have an unsigned value that is 8 bits that can go from a range of 255 to 0, or we can have signed value that goes from 127 to negative 128. So this same binary value of binary 11010100 can be defined as 212 in unsigned, or negative 44 in signed, depending on what it's labeled as. Rust has what are called U8s, which hold 8 bits of unsigned values. Rust also has I8s, which hold 8 bits of signed integers. With that, hopefully you've come out with a better understanding of how computers store numbers. This only covers integers, but there are so many other types of numbers, like floats, fixed decimals, and other things. Stay safe, stay curious, and take care.